psi, and it's an eigenvalue, what happens over here?
Here, constant.
You pull out a constant, lambda, your eigenvalue, and then what do you end up with over here? Psi. Alright, so what you want to think about this is, why do you put it in the middle? Is it because it lets this operator act on the wave function? And when it acts on the wave function, what does it do? It pulls out the value, the eigenvalue if you want, if it's an eigenvalue problem. And then what does it leave you with? Psi again. So what happens is you get A to B of psi star, and then over here you pull out the eigenvalue, so maybe lambda sub I, this is like the eigenvalue, or just the value, times psi again, dx. And now because that's a constant, this comes the integral from A to B of lambda I, psi star, psi dx. And then what is this? This is once again the dp. So this comes the integral from A to B of your values times d probability. Alright?
Would you want the average value of a function versus the average, so f of x, versus the average distance of x, right? They're different things.
Yeah?
Would you just take a second to just give a quick example, like average value of a function? I get average distance x. Average distance x would be like, where on the wall did the particle of light hit, right?
Okay, I'm not sure what your question means, or what you're asking exactly, but we'll try to come up with something here.
To make a verbal distinction, to further develop what experimentally would be the difference between the average value of x versus the average value of the function. Experimentally, what would it look like? The difference.
I'm not sure I know what you mean. The function is x.
Equations 1.17, 1.18.
What is it?
Equation 1.17 versus equation 1.18. Experimentally, the difference.
So, 1.7 and 1.08 is the following. Instead of using I, it says f of x equals the integral of minus infinity of, okay, so here we go. X times
No, right, we did that for homework. I'm just wondering what experimentally is the difference between the two? Like the physical.
Okay, so let me just follow through here a second, okay?
Yeah.
You have that, and then you have the expectation of f of x equals integral of f of x, rho of x, dx, right? Those are 17 and 18.
Yep.
Let's let f of x equal x.
Okay.
Then what does this become?
That's just x.
That's this. So this is just a generalization of that. This is, if you want, this is a general function. This is an explicit function. They're given an explicit function. They work on, just like, remember before I did, we started off with I and then I squared, and we generalized to f of I.
Yeah.
That's what we're doing here. They did an explicit case x and then generalized it to f of x.
So you're saying like f of x would be like x, like a polynomial.
Could be anything. Yeah. Whatever your function is.
Right.
Essentially, it could be a line. X is just,
It could be an elephant.
Yeah.
Okay. So if we do this, so here's our goal. So in quantum mechanics,
The average elephant equals the integral of elephant.
we solve
The
the
elephant.
following. We solve h
The elephant's
psi equals IH partial psi with respect to t.
the probability of creating it out.
Okay? What do we get from there? What do we solve from there? The differential equation, right? We put in H is the Hamiltonian, which represents the total energy, which is the kinetic plus the potential. Put that stuff in for whatever potential we have. What do we solve from here? We solve psi. We solve for the wave function psi. Okay, so we get a nice answer. It looks like this. Psi looks, here's 0, here's L. Psi looks like this. This is psi. So I'm just going to do psi. By the way, Charybdis makes very nice designation. Psi of x only equals baby psi. Alright, and I'm going to use that a lot. Okay, so that's that. Once I have psi, what do? I say, what the hell is psi? I don't know. What do I know?
Hamilton.
Square psi. So then over here, I come over here and I plot psi star psi of x. And that's going to equal this then, right? 0 to L. So quantum mechanics, say electron in 1D trap, it extends from 0 to L. So this is, I solve the wave function for an electron in 1D trap. We'll got, a lot of the work is solving that, but let's say we solve it, we come up with a wave function that looks like that, then what can I do with it? I go psi square psi. This is a probability density, right? Okay, once I have a probability density, let's ask some questions. Where is the particle?
Probability is that 1 over 2.
Okay, so the first question is that I want to ask is, where is the particle? Okay, now look, if I just did the integral from minus infinity to plus infinity of psi star psi dx, what does that equal to? 1. Alright, so that doesn't tell me where it is. But check this out. What if I did this? What if I said, what is the average or the expectation value of x? That's going to equal the integral from minus infinity to plus infinity of psi star x psi dx. So what is this asking me? So everywhere it's saying, okay, what is the probability when I'm right here, multiplying that up? What is the probability when I'm at x equals right here? I'm integrating over x now.
Yeah.
So what will this give you, the average of?
Where you find them.
This is where you would find, okay? It's the average value where you would find it. So it's the average value or the expectation of where you would find it would measure a particle. Okay? Now, let me be clear. The expectation means what? It means an average. So this is the calculation. This is what the words you were using before. All right? What you have to imagine that this calculation is that it is an infinite number of identically prepared ensembles of this situation. And if an infinite number of measurements